Friends, welcome to Mickey Techie. I would like to thank my family for their continuous support for creating these kinds of video, and I would like to thank my mentor Professor R. Surendran from Government College of Technology Coimbatore, and I would like to thank Almighty for supporting me, and I would like to thank all my subscribers and followers for their continuous support and motivation. Today's topic is Mohrs circle. The Mohrs circle is the graphical representation or a graphical method for finding different kinds of stresses acting in a body when the body is subjected to mutually perpendicular or an oblique stresses. Here, what are the stresses when the body is subjected to oblique, uh, oblique loads or a mutually perpendicular loads means they have a major stress, minor stress, principal stress, and normal stress, shear stresses, tangential stresses. Likewise, the different kinds of stresses are acting so that it is a graphical method, it is a simple and graphical method for finding those stresses in very accurate as well as very simple manner. Okay, before seeing the Mohs circle, we would like to see the what is meant by principal stresses and strain. In simple, the principal plane which have no shear stress, a plane which have no shear stress is called as a principal plane, whereas the principal stress is the magnitude of direct stress across a principal plane. So direct stress means in the plane there is no shear stress where the normal stresses are exist. Therefore the principal stresses is the magnitude of direct stress across a principal plane is called as a principal stress. We are going to discuss the different conditions of stresses acting on a oblique section. On that, the first one is the stress on an oblique section of a body subjected to direct stress in one plane. We know that for the normal stress the formula is the resisting force by area. The resisting force for a body, the resisting force is equal to applied force. Therefore we call it as an say in a formula force by area. Here, take a rectangular section, the consider only the normal stresses or a direct stress of sigma is acting as a tensile in manner. We have a ABCD of a cross section, and the force, the plane which is theta, from there it is having a stress plane, it is an oblique section plane. Let me explain in by means of let me explain by means of the drawing. So this is the oblique plane, and these are all the stresses acting as a major and minor stresses. Here, the normal stress is equal to force by area, as we know that force, that is sigma into A cos theta divided by area is the A secant theta. We know that cos by secant is equal to cos square theta. Therefore, normal stress is equal to sigma into cos square theta, and the tangential stress is the stress across the section. So here you can see the across the section. Here this is the across the section tau. The tau is the force along EF section, and therefore divided by sigma into A sine theta is the value divided by area of EF, that is A secant theta. Here sine by secant is equal to sine 2 theta. Therefore sigma 1 by 2 sine 2 theta. Therefore, sigma by 2 sine 2 theta is the value. The maximum normal stress sigma n is equal to the sigma cos 0. That means at the plane of 0 degree, the normal stress on an oblique section will be maximum. Therefore, theta becomes 0. Therefore, the normal stress is equal to sigma. Where the maximum shear stress, you have to understand that the shear stress is always perpendicular to the normal stress. Therefore, if the normal stress acting on a plane is 0 degree, then the shear stress is acting on a plane is the 90 degree. Okay, whereas here you have to remember a point, the shear stress is maximum at the two planes. The two plane angle is 45 degree and 135 degree to the normal section. Therefore, here the shear stress is acting at 90 degree plane. Therefore, sine 90 is equal to 1. Therefore, tau max is equal to sigma by 2. The resultant stress is equal to sigma r is equal to the square root of normal stress square plus shear stress square. This equation is hold good for the compressive stress also. And next is the obliquity. Obliquity means the resultant stress acting on an angle. Okay, therefore tan pi is equal to tau by sigma n. Tan pi is equal to tau by sigma n. I hope that you have cleared the first condition. We continue with the second condition. Okay, the second condition is stress on an oblique section of a body subjected to direct stress in mutually perpendicular directions. Here, the mutually perpendicular directions is sigma x and sigma y coming to picture. Here, the sigma x is acting on the longitudinal axis of tensile, as well as sigma y is also acting in an it is perpendicular to the longitudinal axis of a tensile. Here, the similar plane of an oblique plane is considered EF plane is considered, and there is a normal stress is acting in this way, X plane, and also shear stress is acting perpendicular to the normal section of tau. We know that the normal stress here, normal stress is equal to force by area of the oblique plane. Here, after simplifying all the things, sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta, and shear stress tau is equal to sigma x minus sigma y sine theta cos theta. That is equal to sine theta into cos theta is equal to sine 2 theta by 2. Therefore, sigma x minus sigma y by 2 sine 2 theta, and the resultant is sigma n square root of sigma n square plus tau square, and sigma r is equal to square root of sigma x cos theta the whole square plus sigma y sine theta the whole square. Here the maximum shear stress is equal to sigma x minus sigma y by 2. And the third condition is stress on an oblique section of a body in one plane accompanied with a complete shear stress. Here is a new condition that the oblique the oblique section of the body is subjected to both normal stresses as well as shear stress. Here, if the shear stress here is giving, we have to put a shear stress like this the secondary stress is called as complementary shear stress. In order to manage the shear stress, we are making two shear stresses in the opposite plane. Here, for the same thing, the normal stress sigma n maximum, here the maximum and minimum stresses are come into picture, where the sigma n max is equal to sigma x by 2 plus 1 by 2 sigma x square. square root of sigma x square plus 4 tau xy, or we can say as sigma x by 2 plus square root of sigma x by 2 the whole square plus tau xy square. In the minimum stress, instead of plus here we put a minus. Okay, sigma x by 2 minus square root of sigma x square by 2 sigma x by 2 the whole square plus tau xy square. Similarly, the tau max is equal to sigma n max minus sigma n minimum divided by 2. Therefore, tau max is equal to 1 by 2 square root of sigma x square plus 4 tau xy square, or we can say it as tau max is equal to square root of sigma x by 2 the whole square plus tau xy square. The next is an most of the exams and interviews we can get this condition: stress on an oblique section of a body subjected to direct stress in mutually perpendicular directions accompanied by a simple shear. And also these conditions are supposed to be acted in the normal life situation also. Most of the components and most of the materials by means of an these mutually perpendicular direct stress and shear stress conditions. So most of the designs are considered these conditions. So here it is very important. That is, the body is subjected to stress in both directions x and y, also accompanied with the shear stress. Okay, here is the oblique section, this is the normal stresses, and this one is the shear stress. The normal stress sigma n is equal to sigma x plus sigma y by 2 plus or minus square root of sigma x minus sigma y by 2 the whole square plus tau xy. Here the plus or minus symbol indicates when the positive indicates the maximum or a major stress, or minus sign or minimum indicates the minor or a minimum stress, minimum normal stress. Here the maximum shear stress tau max is equal to sigma n max minus sigma n minimum divided by 2, that is tau max is equal to square root of sigma x minus sigma y by 2 the whole square plus tau xy. Next, the Mohrs circle, it is a graphical method. As I already said that it is a graphical method of finding normal and tangential and resultant stresses on an inclined plane. The maximum shear stress will be equal to the radius of the Mohrs circle. This is an important point. You have to remember that the radius of the Mohrs circle, is equal to maximum shear stress acting on a body, where the maximum shear stress is acting at the 45 or 135-degree angle to the principal plane. Okay, I hope that there is a key points in the Mohrs circle. I hope that you have all taken the notes, but these key points will give a summary of the Mohrs circle. Let us discuss the key point in the Mohrs circle. The first key point is the when a body subjected to a direct tensile stress of sigma in one plane, the maximum shear stress tau is equal to half that of the maximum normal stress. In the first condition, we have discussed this. So, this is for your reference. And also, the second key point is maximum shear stress is 1 by 2 algebraic sum of maximum and minimum normal stresses. The fourth condition will represent this. And again, and the key point number 3, radius of the Mohrs circle is equal to the half the difference of two principal planes. Yes, we know that radius of the Mohrs circle is equal to maximum shear stress acting on the body. The maximum shear stress is tau max is equal to sigma n max minus sigma n minimum by 2. That is half the difference of principal planes, stresses in the principal planes. The key point number 4 is maximum shear stress is equal to radius of the Mohrs circle. And key point number 5 is Mohs circle is used to determine stresses on the oblique section of a body subjected to direct tensile stress in one plane, direct tensile stress in mutually perpendicular planes, and direct stress in the mutually perpendicular plane accompanied with simple shear. Next, key point number 6. The extreme of any diameter of the Mohs circle represents normal stress on the plane at 45 degree. Next, for the different conditions, how we can take as a Mohs circle that we have to discuss. If the torsion of shaft, the representation is like this: a square accompanied with the shear stresses. That is, it is pure shear. The Mohs circle follows a complete circle between x and y axis. Next is the tie bar subjected to tensile force. We know that tie bars are used in screw jack as well as in the power screw applications where the tensile force is predominantly acting. Therefore, tie bar is subjected to tensile force that is represented in a square column, a square of both tensile forces acting. Whereas thin cylinders subjected to external pressure, it is represented by means of a square of all sides of a tensile stresses. Next is a shaft subjected to combined bending and torsion. We can give in a fourth condition of we discussed. Body subjected to both both normal stresses as well as the shear stress. Here, I would like to make a key point number 7. The state of shear stress in two dimension at a point in a load component can be completely specified by indicating the normal and shear stresses on mutually perpendicular plane passing through a point. Next, key point number 8. Key point number 8 is in two-dimension problem, state of pure stress is at a point. As we said, the state of pure stress here is a circle where pure stress condition, two-dimension problem, pure stress condition, the circle becomes a point. Here, the point says that strain in x direction is equal to minus strain in y direction, that is eta x is equal to minus eta y, and shear strain gamma xy is not equal to 0. The center of the Mohs circle can be found out by r is equal to sigma 1 plus sigma 2 by 2. I hope that you have all enjoyed the video on Mohs circle. I hope that the knowledge can be transferred. Knowledge that I have can be transferred, is been transferred. Thank you. Thank you all. Thank you for supporting my video. If you have any doubts, let me know in the comment section. I will put another video for your doubts. Thank you.